Hello everyone, this is our Unit 1 Lesson 2 video. Moving right along here. We went over a few different kinds of graphs in Lesson 1, the dot plot, and a little bit about histograms. But here's a type of graph that perhaps you have seen maybe a few times before, but may not have had a lot of experience with. And this is something called the stem and leaf plot. So the stem and leaf plot is a very unique kind of graph in the way that it showcases data not with points, but with the actual numerical values themselves. Much like a dot plot, it will be a very good way to see grouping of data, um, but you're not actually drawing a graph. You're analyzing and organizing the numbers themselves. So let's take a look and see what that looks like. Okay, whoa, this is an interesting picture. Okay, this is what we call a stem and leaf plot. And so you'll notice right away that there's a dividing line and then there's numbers on both sides. Okay, so on the right side of the graph are stems. Or sorry, on the left side of the graph, these are your stems. And what they represent are digits of a particular data point. And on the right side, we're going to call these leaves. Almost like you have a branch sticking out, and along the branch, there are different leaves coming off the branch. So think about it that way, or like each one is a vine, something like that. Very natural looking. Okay, but let's see what this data is actually saying. So this particular graph represents the number of accidents per 1,000 people for 40 years and 40 careers in 1 year. So in other words, here we're collecting some data representing just an accident rate in different careers. So each one of these numbers represents a career. So now in this particular case, so accidents per 1,000 people, so some of them have zeros. Okay, so maybe no accidents. Well, that's a good thing. And then there's nines, but the nines are all spread out. What gives? Okay, so here's what's happening. Um, in a lot of times in data, what you'll see is a lot of repeated numbers. And so what this graph does is it tends to shore up some of those repeated numbers. And I'll give you a point here. So the stems refer to the actual tens digit of this particular data point. The leaves refer to the ones digit. So when you see a 4 on the left and a 3 on the right, what this actually represents is the data point 43. The next data point after that happens to be the point 67. So 43 accidents per 1,000 people, 67 accidents per 1,000 people. Now, you may wonder, why would we do that? Why would we split it up? Well, let's look at the 7 row. The 7 row represents 70s, and this represents the data points 75, 76, 76, 76, 77, 78, and 79. So the idea being that all of those data points, not only would they just naturally be grouped together in like the 70s row, if this were a bar chart or a dot plot, we would probably do that. But the data just has a lot of sevens in it, and we're pretty clear that like each one is 70 something. The next one, the next row would be 84, 84, 85, and so on and so forth, all the way up to 3 copies of 89. So when you have a data set that has a lot of repeated values or values with a lot of similar digits, what this does is it organizes it by the last digit of that data point. And by doing so, it basically turns the last digit into a dot. So think about this as a dot plot, but vertical. And each one of these represents the last digit of your data point. Most of the time, it's going to be the one digit, but there are times where you may have like the 10th digit or something else. So it makes it a very kind of interesting way to kind of see the numbers um, in groups, because if we did this on a dot plot, the biggest difference would be that um, on a dot plot, we would have dots stacked to 84, a single dot at 85, a dot stacked to 86. And what would happen is these columns would be very, very small. And you'd have a lot of columns, but just very small. And you wouldn't really be able to get a chance to see a lot of the trend in the data. By using kind of like the power of a dot plot, by having each number visible, and at the same time having the benefit of a histogram where the data is clumped into ranges for ease of seeing it, you know, I think you get the best of both worlds and you end up with a really powerful graph. Now, in this graph, as you can see, it's actually really easy to see things like the shape, the center, and the spread. So we can find a lot of those values here. So let's clear this away so you can kind of see. Again, we'll still write up here. I like to write tens and ones, kind of like a key to know what they refer to. Okay? So the optimal stem and leaf plot has somewhere between 5 and 20 leaves. Too few leaves, and all your data just ends up in a big row. Too many leaves, and you end up like you would with a dot plot where you have just lots of buckets and only a couple points in each bucket. So we try to aim for, if we can, between 5 and 20 leaves. Okay, let's think about this. So what would typical values be in this data point or in this data chart? So here it's really easy to see that because each number is represented, 76 looks pretty typical. 88, 89, 90 would be typical. So perhaps if you want to know what like a typical range is going to be, for a typical range, I might say something like, you could say like 80, like 76 to 90, something like that. You could even say 84 to 90. You could say 76 to 99. All of these numbers are defendable as far as what we would call typical range, or some other combination thereof. Um, Remember that typical usually happens in a range because we want to know, like, where approximately would we find um, any particular point in my chart, like a common value. And with some data sets, like if I were to compare this to another data set, you might find that some similar numbers, but not exactly the same numbers, are typical. So by illustrating as a range, we're saying to ourselves, you know, generally for a data set like this, we will have similar data in about this range. So again, stats is not ever really definitive, but a lot of times we make statements that we can at least comfortably defend. Now, so let's look at this chart. Notice it goes all the way to 15. So my highest value is 152. So I would see this and I would look at this and say 152. And I know that this appears to be an outlier. How would I know that this is an outlier? Because I got a big gap in between there, right? The last data point is 109. 109 to 152 is a pretty big wide jump. So I'm comfortable saying that that's an outlier. Now, how do I find things like median? Well, that's easy, right? 40 careers, cut it in half, that's 20. So we're going to go 20 points in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. So the median is 89. It's be in between the 20th and 21st points. So the median, easy to see in a chart like this. So, I think there's some power to it. All right, so there's a couple of different ways that we can look at a stem and leaf chart. Okay, if you have data with decimal points, you can do much the same thing. but you use the ones as the stem and the tenths as the leaves. So it might look a little bit like this. You might do 9, 10, 11, 12, 13, 14, 15. I know I'm writing over the words. 9, 8. And so here you would have ones, tenths. And when you see a 9 and an 8, you would automatically read this as 9.8. And notice that I don't put the decimal point when I do this. I suppose you could, but again, with the whole repetition piece that stem and leaf plots are trying to avoid, there's no reason to, because we're already remarking that this is the tenths place. So there's 8 tenths. There isn't 0.8 tenths, just 8 tenths. So the next one would be 11 and 1, 12 and 1, 13 and 4, and so on and so forth. So we can do a chart that way. Now, suppose we have data sets that we'd like to represent as a stem and leaf plot, but where the data is a little too compact. For example, this one. You have data that's integers, and it's within a range of 10. Now, I can't put this in a stem and leaf plot normally, right? Because what ends up happening is everything ends up on the same stem. I'd have a tens digit of 0, and after that, I would have just this whole string of numbers, in order, of course. What we do instead is we can break this apart. To create a plot with 5 stems, we would need to break it into groups of 2. Well, how do we do that? Like this. So here's a fancy stem and leaf plot that we can do. So this one is a little unusual, and you're going to notice the different letters here. So 0 might represent 0 and 1. 0t for 2 and 3. Do you see why we're using t? Because 2 and 3 both begin with t. That's a nice coincidence. 0f for 4 and 5. Hey, coincidence, they both begin with f. 6 and 7 begin with s. And then 8 and 9, you could use whatever symbol, but we know it's the last one. A lot of times we'll use an asterisk. And actually, kind of think about it like asterisk on a keyboard is Shift 8. So that's not too bad. So here's an example of what a stem and leaf plot would look like using this kind of setup. And you'll see down below here. If I have a data set that's just compressed in this really tight range, but I still want to see like the shape and the spread of that data, notice how I have the 0 only contains 0 and 1. 0t only contains 2s and 3s. 0f only contains 4 and 5. Now, if I had to continue this chart, the next one I would put would just be 1, like this. And if I had, say, 1 and 0, 0, 0, 1, like this, then I'd have 3 10s and an 11. And then after that, if I have 1t, then this is going to represent something like this. It might represent 12s and 13s because the ones digit represents the 10. So 12, 12, 12, 12, 13, 13, 13. So in this particular case, here we still have 10s and we have 1s. Now, I'll admit, this is kind of fancy, and you're not going to see this all that often. Try kind of threw that one at you just to see what you'd think of that one, but there's one that's a little bit easier to do too, which I think I can just put this on a separate page here. So again, if you have a data set that has a little bit of range to it, right? Say you have the numbers, let's say 3, 7, 11, 15, 9, 21, 426, let's say 19 and 13 and another 15, let's say. Okay, so let's say we have this data. So again, if I try to put this into a stem and leaf plot, okay, I might have tens and I might have ones. What will it look like? Well, my tens digit for some of them is 0, and I have a 1, and I have a 2. And I could put that on there, and it might look like this: 3, 4. Now I go to ones. Which ones are my ones? So I have 11, 15, 13, 19. So I have an 11. I have a 13. I have two 15s, and I have a 19. Notice how I didn't have to write the 1 all but just the first time. And then I have a 21 and a 26. So maybe this data is all right. However, if I want to hold myself and say that I need at least 5 stems, one way that you can break down categories like this, sometimes it's useful to just break them in half. And what we can do is we can break it down to what's known as low and high. So I'm going to draw the same chart, but this time, here's tens, ones, but what I'm going to do is I'm going to call it 0L and 0H, 1L and 1H, 2L and 2H. So here's another way to break tens down. Now, what do you think I mean by L and H? I mean like lower values, higher values. So lower single digits, higher single digits. Lower teens, upper teens. Lower 20s, upper 20s. Kind of like a weatherman might say, okay? So the lower values here would be any values from like 0 to 4 would go in the first row. And then for the uppers, maybe 5 to 9. 10 to 14, 15 to 19, 20 to 24, 25 to 29. So we're splitting each range in half. Maybe this one is a little bit easier to work with. I know the other one, you might see that every now and then. So certainly keep an eye out for that. But this one, could be a little bit more useful, especially if you're used to thinking like uppers and lowers anyway. So if we were to make the same chart, let's see what would happen. 3 and 4 are both lower single digits. So we'll put 3 and 4. Do I have, I forgot a 9 here. Do I have any higher digits? I have a 9. Oh, and it looks like I have a 7 too. Oops, I forgot the 7. Oh my goodness, what am I doing tonight? All right, so let's get rid of that. Okay. 7, 9. I'll do the same thing over here. I just forgot a couple. Okay. So what about one lows? So one lows would be 10 to 14. So I've got an 11 and I've got a 13. Again, notice that I only write the 1 and the 3 for 11 and 13. Do I have anything 50? I have two 5s. I have a 15, a 15, and a 19. Do I have some lows? I have a 21 and a 26. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. All right, this time I got them all. Sorry about that. Well, anyway, you can tell how both graphs might tell you a similar story or perhaps maybe not a similar story. So in the original graph here, you can kind of see how it's somewhat symmetrical, but maybe not quite. Here, the symmetry is still approximately there, but you get a little bit of a better sense of where the typical values really are in that group. So it is useful in order to add a few extra stems to be able to do this when you need to. Okay, so that's really it for drawing that graph. Okay, so as I've said before, outliers show up really easily. So outliers are separated by at least one or two empty stems. Um, there are some technical definition of outliers. So here, this graph has no outliers, but the previous one that we did here, this one clearly has an outlier. Now, what about the 43? Is that an outlier? It does have a gap here, so maybe that's an outlier. That's something we'd have to check later. Okay, so here's a good plan. Like, when do we really want to use a stem and leaf plot? So, numerical sets, small and moderate number of observations, um, and especially when you really want to know things like the shape and the spread of the data. So, like symmetries and shape. You can still find the center and median perfectly fine, but really what you're looking for is how it compares to all the other data points. Okay, so essentially, select a digit as the stem, list all the possible stems in a vertical column, and notice that, as you saw, I included intermediate value stems that have no leaves. So when I went back here and I looked at my original plot here, I had no numbers in the 50s, but I included a 5 anyway because I want to leave a space because maybe I'll get data in that area. Maybe I will increase my sample size and collect data here. But more than that, I want my data to be scaled properly. If I didn't include gaps, I would never be able to see outliers. That's a bad thing. Outliers are important. Okay, so list possible stems in a vertical column, include intermediate values, record each leaf next to each stem, and so each leaf is essentially the last digit of each data point. So last digit of each point. Include a title and a key for good measure. Enjoy while hot, serve 72. Why 72? Why, that's you. 72 students in class. Okay. That's pretty much it for this. It's a quick one because we're just going over the one kind of graph. Um, we can do a little bit of a practice here, and we'll be on our way, it looks like. So let's go ahead and give it a try. All right. So we're going to construct a comparative stem and leaf plot for annual delay per traveler for each of the two different sizes of urban areas. Okay. A report titled Congestion Reduction Strategies included the accompanying data on extra travel time for peak travel time in hours per year per traveler for different sized urban areas. So this is extra time that people have in their year just based on traffic. Yikes. Ooh, I don't want to be here. Yikes. Okay, very large urban areas, large urban areas. Okay, so really there's a statement that researchers make here. The larger the urban area, the greater the extra travel time during peak period. Well, let's find out. So what we're going to do is we're going to construct what's known as a comparative stem and leaf chart. And a comparative stem and leaf chart allows you to put two different charts on the same axis so that you can compare them. Well, how do you do that? So let's start with the first one. Looks like my stems, if I use tens and ones, I can use tens and ones here. Looks like I go from 3 to 9. So let's do that. So I'm going to do 3, 4, 5, 6, 7, 8, 9. Okay. Now the lovely part is my data is in order. So I can just go ahead and put the data in. So again, remember, we only have to write the ones digit for each data point. How nice is that? It allows us to put it in very easily. 72, 93. Okay, easy. All right, let's take a look. Um, what do we say? Does the data look approximately symmetrical? Yeah, pretty close. One minor outlier here. We can decide whether that's an outlier or not. Something to keep in mind. Okay, great. So now here's my question. What do I do with the other side? Where do I put, if I want to use the same, if I want to use the same scale to compare the two data, how do I do that? I put it on the other side. So what I'm going to do is I'll use my mouse for this. I'm going to move this up. Oh, can't do that. Looks like I'll have to erase. Okay. Oh, there we go. Oh, gotcha. Okay. Okay, perfect. Oop. Okay, so it's doing something funky. I hope that... Oh, looks fine. Whew. Thought I was going to lose the video for a second. Okay, so what I'm going to do is we're going to add the missing stems that we need. So the missing stems that we need here looks like we need a stem for 1 and 2 to cover this data set. So let's go ahead and do that. Okay. Having some lag time here. Hang on. There we go. Oop, it's coming back. Oh, I think I just think that was my hard drive that spun up. Okay, that's fine. Or not. I'm having some issues. Okay. Looks like we're having a little bit of difficulty here. There it goes. Okay, so 1. Perfect. Whew. All right, so let's extend this down. Okay. It's going to show up in a second. Okay, I don't really feel like you losing the work that I am doing here, so I'm going to have to kind of make this quick. Okay, so it doesn't look like it's going to let me write the rest of it here, but oh, we have a 0, we have a 2. Hey, look what I'm doing. I'm writing it right to left because I'm extending outwards from the stem. So that's exactly how we do a comparative stem and leaf chart. So we're going to have a 3 and a 4 and then a 7. Come on. I put a 4 there. Come on. Okay, so looks like I'm starting to lose this here. So I'm gonna kind of have to end things pretty quickly here. So before I lose all of this. So here's what's happening, guys. Notice that what I'm doing is writing the leaves from right to left outwards from the stem. So you'll have a 0, 2, 3, 4, 7, 8. On the 2 line, you're going to have 3, 6, 9. And then you're going to have 30 or 0, 0, 3, 3, 5, 8, and so on and so forth. So you're going to fill the chart out this way. And as you do, you'll be able to answer this question. So see if you can go ahead and fix this, and we'll cover this one in class. But you can also see from the data what you think is going on. The larger the urban area, the greater the extra travel time during peak period. Does that make sense? I think it's going to look like it to me, especially when the highest number here is 55. So all this data is going to kind of go all the way up to here. All right. So I think I'm going to leave this video here because I'm about to think this is about to conk out on me. I don't want to lose all this work. So we'll leave it here and we'll go over some more stem and leaf plot in class. All right. Have a lovely evening.